Hi everyone, today we're going to look at orbital motion. Now, orbital motion is circular and it's the path that a body takes around another body. Now usually those objects, there's a large one and a smaller one. For example, we could have a satellite that goes around the Earth in orbit. There could be a space station or the space shuttle when it was in service. It could be a moon. Now the moon's a little bit bigger than an artificial object, but the moon is smaller than the Earth and it has an orbital motion around the Earth. Similarly, we have other moons around other planets. Jupiter and Saturn have lots of moons, whereas Earth has one. Mars has two little rocks, Phobos and Deimos. Uranus and Neptune have several each as well. So moons go around planets in orbital motion. Planets go around stars in orbital motion. Our Earth is in orbit around the Sun. And just as we have the scaling up, stars too in orbit around the centre of the galaxy. Okay, we reckon, or we theorise and we think with pretty good certainty that there is a supermassive black hole at the centre of our galaxy, providing this gravitational pull for the stars to go around it. But let's begin looking at orbital motion in a rather strange place. We're going to look at this. Here is a little animation. I don't know why there's a statue down there with a guy with boxer shorts on. I think it's a famous statue in Rome. Anyway, for details. We have a cannon. The cannon, the centre of the barrel of the cannon is 5 meters from the ground. We have a target 15 meters away, so we'll put it right there. And then we have an initial velocity, that's a horizontal velocity. It's going to come out flat, and gravity will pull the object down. So if I fire it like this, then I get the target. So what's happening there is, as the projectile is fired out horizontally, it maintains its horizontal speed or velocity, but it drops. It drops due to gravity. And what I'd like to show you is that these two velocities, the horizontal and the vertical, are completely independent of each other. So if you fire a cannonball straight up, it goes up and down. There's zero horizontal motion. It goes up and down where it started. As soon as you fire it at an angle, then this happens. And so you have a combination of a horizontal motion and a vertical motion. Now, it doesn't go as high, and I might think, well, that can't be the case because it's not going as high as it was originally. Well, what happens is the vertical motion is affected by gravity, the horizontal is not. The horizontal velocity or speed never changes, so in here it's 15 and it comes out at 15 and stays at 15. But notice as it's travelling at 50 meters per second horizontally, it's falling due to gravity. Now if I raise the angle a little bit, then say we raise it to 25 degrees, then as it comes out at 15 horizontally, it goes much further. Now it's still travelling at 15 horizontally, but because there's a little bit of vertical motion upwards, that's the same as perhaps throwing a ball up in the air. It will take longer to go up a little bit, then stop, then fall to the ground, as it would if you were just to drop it to the ground. So if I set it to 0, that's the equivalent of dropping it to the ground vertically. So it just drops to the ground at the same time as it's moving horizontally. But if you fire it up a little bit, so say you give it an initial vertical velocity upwards, then that's like throwing the ball up, then it's going down, all the same time as it's going horizontally. Okay, so let's clear these for a minute. I want to show you this really quickly. I reckon if I put this down to the ground, I'm going to put it to 0, just put it flat on the ground. There we go. 30 degrees will fire the cannonball a distance of, well, it goes to there. Well, you know the distance. It goes that far. It goes over the target because it has this initial little vertical motion up. But if I fire this at 60 degrees, like so, I reckon that it's going to go the same distance. There we go. Now, how do I know that? Well, I know that when we divide up, or when we split the initial velocity into its components, then we have a horizontal vector and a vertical vector. There's a little bit of clever maths going on here. Sine of 60 is the same as cos of 30, and sine of 30 is the same as cos of 60. So I know that these motions are going to go the same horizontal range. Anyway, we're getting a little bit confused by details here with projectile motion. Needless to say, I want you to take from this that if we have an initial vertical velocity horizontally, it's going to fall to the ground. And if I raise this a little bit higher, then as it falls to the ground horizontally, it's going to go a little bit further, because it's like dropping a ball from a higher height. The time it takes to hit the ground will be longer the higher you drop it from. So in the same time as it's dropping to the ground, my horizontal velocity is reaching further along. So I want you to know that. If I raise the height, then I fire it horizontally. Equally, let's go back down to, is that a reasonable value of 5 meters? Let's go to here, erase all those. If I have a low velocity, like so, then it comes out reasonably short. So the same height we're looking at here. So in the time it takes to fall to the ground, it travels this far horizontally. If I increase the speed, then in the same time it takes to fall to the ground, it will travel further. And as I increase the speed more and more and more, then you'll find, I want to raise these ones then, that as I increase the horizontal velocity, it takes the same time to fall to the ground, but as it's doing so, it will reach a greater horizontal range. Okay, now that's a very important principle. So this projectile motion of horizontal velocities and vertical velocities, and the combination of the two, is very important to the question, which is, how do things move in orbit? So the question I want to ask you first of all is, how does a rocket get into space? Now, you may be surprised to know the answer is, it's not what you think. It's not straight up. You normally launch rockets as close to the equator as possible. The reason being that you are on the surface, or part of the surface of the Earth, that is travelling the quickest. Now we'll pause there for a second, we'll come back to this photograph. What do I mean by that? So let's take a picture of the Earth, and the Earth is spinning. So let's imagine this is move my microphone over here a little bit so I'm within earshot. There's north and there's south. Now we should know from year 7 that actually the Earth is tilted by 23 degrees, so it rotates around its axis that way, but let's just deal with it this way for the moment. It spins, it goes round. Now if you were to stand on the equator, okay, what would your speed be? Now let's just pause for a second even more. What do I mean by speed? Well, I'm sitting at my chair at my table just now in my kitchen, and I don't feel like I'm moving. Relative to my table, I'm not moving. Relative to my garden and the outside, I'm not moving. Relative to, I suppose, the rest of Earth, I'm not moving. But relative to the centre of the Earth, I am moving quite quickly. Okay, the centre of the Earth at the centre of this ball that's spinning, and you'll be quite surprised to find, so we do a little bit of maths, if we assume that the radius of the Earth is 6,000 kilometres, or 6 million metres, that's a big approximation by the way, then my speed on the surface of the Earth at the equator, remember this is the equator, is 400 36.3 meters per second. That's how fast the Earth is spinning, and therefore things on the surface of the Earth at the equator. Now we live in Winchester, which is a latitude of 51-ish degrees. Now we're not spinning as fast, so we're going round this way at this altitude. We're not spinning as fast as we would down there. The whole Earth is spinning in 24 hours, so the further north you go, or south I should add, you will spin a little bit slower. Now at our latitude in Winchester, our rotational speed, the speed that we travel at on the surface of the Earth, is 274.6 meters per second. And just for completeness, if you were to stand on the North Pole, which is straight up at 90 degrees, then your speed would be 0. You would be spinning on you'd imagine the Earth spinning below you. You'd just be rotating around on the spot. Okay, so that's the speed at the surface of the Earth, and that's an important principle because we sort of consider the centre of the Earth to be the source of gravity. Again, it's not quite this picture, but we'll assume it is just now. So gravity is there. We are 6 million meters away from the source of gravity. In Winchester, we're a little bit closer because the Earth bulges out of the sides, but we're up here and we are a little bit closer, but we're still about 6 million meters away up here. So things that move in a circle this way, we need to deal with radius or radii and circles. So get a few things in our brains first of all. Circumference over circle is equal to 2 pi times the radius. That is an important little equation that we'll use later on. So, things that move in circles, we have to deal with the circumference, we have to deal with the radius, and that's just a couple of little factoids there about how fast the Earth is spinning at those particular points. This is the reason why it bulges out in the middle, because it's going so much faster. Less so Winchester, and it's spinning in the spot in the North Pole. But the radius of the Earth is approximately 6 million meters at every point. It's a little bit more, it's probably about 40 kilometers further out here than it is at the North Pole. We are probably about 15 kilometers further out, so it changes, but to be honest, it's pretty close to 6 million meters everywhere. Okay, so let's now go back to this. This is a nice little image of the space shuttle at launch from Florida, Cape Canaveral. Now, I've seen people class to say that this is a fake picture. It looks like a miniature. It's called the diorama effect, where it takes real objects and makes them look as if they're miniature. I think this is an amazing picture. This is the space shuttle there, and it's taken from a high altitude plane that NASA have to monitor space launch. And I want you to notice that it's not straight up. Okay, so the shuttle does not launch straight up. It actually launches up and then travels east. Now, if anyone was fortunate enough to watch some of the SpaceX launches recently, I think it was back in April, no, May it was, there was a rocket launch from over America, over the East Coast, and I saw it fly overhead. The path of it took over London about 10 to 15 minutes later. It's going that quickly. And so now we need to think about why it has that shape. So here we have the ground, and the rocket does not go straight up. Okay, it doesn't go straight up. It doesn't do that. What it does is it goes up in this path here, so that when it gets up into space there at altitude, it's traveling fast enough horizontally. Now that brings us back to our little projectile animation, which is oh, where is it? It's here. Okay, we need to be flying fast enough horizontally for a particular reason. Now let's explore why this is rubbish for rockets and this is essential. If you fire the rocket straight up, once you burn out the engines, it will just fall straight back down. But here, if you fire it up horizontal, so it curves and it's going flat, parallel to the Earth's surface, once the engines burn out, hopefully you're doing around 18,000 miles per hour. And that's the altitude of the space station, which is around 200 miles. That's a critical altitude to reach, and that's a critical horizontal velocity to be reaching. Now let's explore why, and once we understand this, we will understand orbital motion. Okay, so here's the thing again. I want you to imagine now, as Isaac Newton did years and years and years and years ago, about a huge cannon on the top of a mountain. And he proposed that he took this cannon and he said, right, here's a big mountain and here's my cannon. And Isaac Newton said, if you fire a cannon horizontally with a reasonable velocity, then it's going to come out horizontally and fall to the ground. Just like here. It comes out horizontally and it falls to the ground because gravity pulls it down. And Isaac Newton said, well, what happens then if we have faster and faster and faster initial horizontal velocities? And he said, actually, what you'll find is if you fire out faster, then you notice that as you fall to the ground, you're actually following a little bit of the curve of the Earth. And Isaac Newton said, if we fire something fast enough so that when it fell to the Earth, it constantly missed. And he called this orbital velocity. Now this is how things not only stay in space, but how things appear in orbit. Because they are in orbit, because they have a horizontal velocity that is fast enough so that when gravity pulls it towards the center of the object is going around, as it falls to the object, it follows the curve of the surface of the object, or in other words, it falls to the ground and always misses. Okay, it's always falling to the ground, but it's always missing. Now, if you're in the space station, the sensation you would feel is 0g. Now, that is a bit of a misconception. Gravity exists in the space station quite a lot, but the thing is, you have this constant sensation of free fall, and that gives you the illusion that there's no gravity. But because you're falling to the ground and always missing it, so too is the space station around you, that everything that's connected, the air inside the space station and you and the objects, they're all falling at the same rate. So as you interact with things, there's no return force pushing against you, so you can push heavy objects, and that's why you can leave things in the air and they just float. Okay, so that's the experience of astronauts, but it's all because of this. As things fall to the ground, they're constantly missing, but that only happens when you have a high enough horizontal velocity. And so when we come back to this image here, to get something into space is easy, you just fire it straight up. To get something into space and make it stay in space, you have to fire it up at an angle, a curve, so that when you get up to this altitude, you're going fast enough horizontally that when gravity pulls you down, you're always going to miss and you stay in orbit. Now, how do we land? Well, you have, if you're, say you're going around in orbit in the space station or the space shuttle when it was in service, you slow down by applying a thrust in the opposite direction, and that would cause you to slow down a little bit this way. So if I'm at this position here, my direction is there, and I'm being pulled in a curve because of gravity. If my speed was a little bit slower here, so say this was too slow to stay in this path, then I would begin, it's called the decaying orbit, I would begin to fall towards the ground. Equally, if I'm down here and I give myself my rocket or my vehicle a bigger push so that my velocity was bigger than I needed to stay in orbit, then what would happen is I would still curve, but I would curve like this. Okay, so if it's too slow, it would begin to decay and go towards the surface. Too fast, it would speed out away. And this is how SpaceX got the satellites in orbit. They went into an orbit like this, and they went to a further out and further out position by going a little bit faster, and every few days they went round and round and round. Eventually they stopped the thrust, and then they stayed in that wide orbit. Okay, this is also how you get to the moon. So if you imagine the Earth in the moon system, you go round the Earth a couple of times, and then you give yourself a boost, and then you go faster and faster and further out of this. Eventually you'll escape Earth, and then you go down to the moon that way. And the same for the return. You don't just go straight, you go in these circles, and then you escape Earth's gravity a little bit by a thrust, and then you end up with this wide path, and then you eventually get caught in the moon's gravity more than the Earth's. There's a little crossover point where you feel this more than this. You feel the moon more than the Earth. You'll fall into a lunar orbit, and you go around the moon like that. It's very cool. So you don't go straight, you have to go in these big curves. Now, the task for today, well, I'd like to do a couple of things in today's lesson. I would like you to have a look at this. Now this is a little animation. If you need to use a browser, hopefully you have Explorer or something that runs Flash. This is an SWV file. I think it's Shockwave or it's Flash files. You need Flash. And I'd like to show you some of Kepler's laws, orbital laws. Johannes Kepler, I think that's his first name, and Newtonian law as well. And what I'm showing you this for is because I asked you to look at this last week. I asked you to look at the planets. Now I've got a few more planets here. This is the distance in kilometers cubed. This is the time in seconds to orbit the Sun squared. Just for reference, I've got the kilometers here. That's for each planet. So the Earth is on average 150 million kilometers, whereas Mercury is 58 million. And here's the seconds for orbit. Here's the years. This is Earth years. So this distance, this is the distance in what's called an astronomical unit. The Earth to the Sun is considered 1 AU, 1 astronomical unit. So that's given the symbol 1, or given the unit 1. And so we have 1 year for the Earth, 1 AU for the distance. The planets that are closer have the lower AUs, further away we have greater AUs. So the distance from Jupiter to the Sun is 5.2 AUs, or 5.2 times the distance the Earth is from the Sun. The years for Jupiter, the orbital year, is about 12. It's 11 point something, but we'll round up to 12 just now. So these are approximate years. Here's approximate AUs. Now what I asked you to do last week was to square the distance in kilometers. So this is the square of the kilometers, and this is the cube of the kilometers. This is the square of the distance. And when you did these two properties for each planet, and you plotted the distance cubed along the x-axis against the time squared, you got a nice straight line. Now the axes are such that because we have Eris way out here, which kind of skews our graph a little bit, all the planets down to Saturn, I think, are all grouped down here in a little gathering. So what you can do is called a logarithmic scale, which just means that one division could be 1 million, the next division could be 10 million, the next division could be 100 million. Instead of having a regular scale, we have this irregular logarithmic scale along the x-axis and also along the y-axis, and you have this nice straight line. We're not cheating in any way, we're making our axis such that it's easy to spread the planets out. So the distance from here to here is much smaller than the distance from perhaps here to here, just because of the way it's spaced out in the solar system. But the main thing is I want to show you that when you plot all the planets in the solar system, if you plot their distance cubed against the time squared, then they fall along this perfect straight line. Now that is not only because of the sun's gravitational pull, but this obeys one of Kepler's orbit laws. This is the third law, the third Kepler law for orbits. You don't have to know it for GCSE, but I want you to know it as a physicist. And what Kepler's law is, he says the AU squared cubed, so the astronomical unit, the distance from the sun cubed, should be the same as the period squared. Now the way it's all matched up here is, if we look at AU in the year, obviously Earth is 1 cubed is 1, 1 squared is 1, but these numbers approximately match up, and that's why we can have this nice straight line, because it's this, there's a direct proportionality between the distance cubed and the time squared. So you can download this, have a go at it. This is Earth's orbit there. This bar here is called eccentricity. Now eccentricity tells me that a perfect circle has 0 eccentricity, and as I increase the value, we have what's called an elliptical orbit. And elliptical orbits are much more common in the universe and the galaxy than perfect circles, but you tend to find that the planets have pretty circular. Mercury is a little bit odd, it has a slightly elliptical orbit. Venus, almost perfect circle. Earth, similar. Let's just look at Earth up here. Earth is reasonably eccentric, a little touch. So you notice that there are times when the Earth is closer to the Sun than it is further away. Curiously, the Earth is closest to the Sun when we have our winter, and further away in summer. It turns out the distance from the Sun is not as big a factor as the tilt of the Earth is to determine the seasons. So we have different planets have different eccentricities. Mars is reasonably eccentric. Pluto, even though it's a dwarf planet, we still in animation. Let's go back to Earth, and let's just assume that Earth was a perfect circular orbit. So Kepler's first law was just having a look at the fact that planets are elliptical, and I put all these values in. Okay, now when you look at the values change for more elliptical orbits, there we go. So Kepler's first law was the study of elliptical orbits and how we can work out the value, the periods, based on the actual object that's going around a centre and what's called an empty focus. Again, elliptical mathematics is tricky, but it's not GCSE standard, so don't worry about it. Let's just clear all of these. Now Kepler's second law is a very cool one. It's looking at the fact that the Earth, or anything in orbit, travels at a certain horizontal velocity. Remember, as it falls to the object, it goes in a curve. And Kepler's second law says that these sections here all have the same area. Okay, and that's pretty obvious because they're all, let's see, 1, 2, 3, 4, 5, 6, 7, 8. There's 16 of them, so it's a 16th of a sweep. We can adjust the size. We can make those, let's just erase those and start again. Start sweeping. We can have 40 areas. We can have fewer areas. I'll go back to 16 because it's a nice number to have a look at. So we'll start sweeping. We'll erase those and start sweeping there. So Kepler says that these segments of the orbit are identical in area. Now the arc of one of these segments is based on the speed, and these lengths here are based on the radius. Now what happens when the orbit is eccentric? So look what happens here. You'll notice that the arc here is much bigger than the arc here. Now you find that because this is a longer radius, so this length is bigger than the length here, to give it the same size of area, its velocity has to slow down. So this is so if you look at this section here, it's got a small arc and a long radius. So it travels slowly along the arc to define the area, whereas here it's got a big arc and small radius. This area here is the same as this area here. In fact, all these areas are identical in size. And so Kepler proposed that this is the case because as planets get closer to the centre of mass that's going around, they travel faster. Bring it back to there. And let's clear all those and let's look at the third. Now this is the one that I asked you to have a look at. P stands for period, or the time to go around the object. Square of that is equal to the radius from the centre of the mass cubed. Okay, and that's what I should do last week. Now this one's quite cool. Okay, Newton's laws. This is Earth. If we draw some vectors, this is the direction at every moment in time that the Earth is travelling in. Now the Earth travels in a straight line, or at least the velocity of the Earth is a straight line. It spins on its axis, yep, but it travels through space in a straight line, or at least it wants to, because at the same time it's going in a straight line, the Sun is pulling it towards it. Now that looks quite similar to this here. It also looks quite similar to this here. So things that move in circles because they have a horizontal velocity and they have an acceleration towards the centre of the source of gravity, or the force towards the centre. That's why it goes in a curve. If I stick some lines on here as well, then they're at right angles to each other. Now the Earth's orbit is slightly eccentric, so if I make it the real orbit, you notice that this angle between the vectors changes a little bit. The Earth slows down over here, whereas it speeds up a little bit over here. So it's not strictly, the Earth doesn't go at the same speed all the time, but it's pretty close. Whereas if I say had a comet that had a big elliptical orbit, then look at how the vectors change. This one here is always pointing toward the centre of gravity, which is the star, but the speed gets bigger and slower, and then it increases as it goes towards the sun. It gets slower as it goes away from the sun. So this is an elliptical orbit, so the orbital velocity of an object changes because of its eccentricity if it's more elliptical. Okay, so we're not going to look at elliptical orbits. We're going to look at circles, and we're going to assume that the Earth is a nice circle. Okay, so the task today then is, I want you to read through chapter in the book. It starts on page 253 called Circular Orbits, and it goes on to page 254. I'd like to read through it, and I'd like you to have a go at these questions here. There's 1, 2, 3, 4 questions. There's none over the page. Nope. So read through here, make some notes if you want, I don't really mind. but I'm just trying to get you to understand circular motion. Now, I have a question for you, and the question is quite cool, okay? Which means I have to go back to here, and I have to draw another sugar-free. So I have to draw another Earth. So bear with me for a minute while I draw another planet. Now, we're going to look at a satellite, and the satellite is called a geostationary, or sometimes called geosynchronous satellite. Okay, now why it's called that? They're used for telecommunications, for TV, for mobile phones. GPS satellites are quite close to there, so they go around in quite less than a day, whereas these ones, they're called geostationary. They're always moving around the Earth at the same time as the Earth spins. So they appear to be above the same point of the Earth all the time. Now, they have to go around the equator. So they go around the equator, but I want you to work out what the distance is that they have to be. Okay, now I'm going to give you a couple of bits of information. Please remember that the radius of the Earth is approximately 6 million meters. So I want you to work out the altitudes above the Earth's surface that you have to position one of these satellites, so that when it goes round the Earth it stays above the same point. So I'm going to take this diagram and I'm going to look at it from the plan view. So here's the Earth here, and I want you to imagine this is this distance D. There's my satellite. We've got, you know, the little solar panels. We've got a little communications disk, and it's going to be traveling around the Earth, and it's always going to maintain this distance around the Earth, and it has to do that by maintaining a certain velocity. So this is the North Pole. Remember, we're looking down in the North Pole. The Earth is spinning. We'll call it this way. Maybe the South Pole. Then the Earth is spinning this way, and as the Earth spins, so too does the satellite move with the spin of the Earth. So it appears to be above the same position. So my question to you is, if the speed of the satellite, the horizontal speed, is, let me get my number, 3,054.3 meters per second. That's the horizontal velocity of the satellite as it goes round the Earth. I want you to work out the distance. How far away is it from the Earth's surface, so that when it moves in this big orbital path around the Earth here, that it stays above the same position. Now that would bring into play some information. So we need to know some information, which is, how long does it take to go from here round to the same position? In other words, how long does it take to cover this path around the Earth? Okay, so that's called the period of orbit, or the orbital period. I'm going to give you the answer. That is 24 hours. It takes 24 hours to go from here round to the same position, because if you were standing on the surface of the Earth, you would go around the Earth in 24 hours. Okay, so the question is, if that is the speed of the satellite as it goes round the Earth, and it takes 24 hours to go around the Earth because it's staying above the same position of the Earth as it moves around. That's how long it takes to go around in this path. My question is, what altitude do you have to set it at to make it work? Because if it was too close, it would be too quick and it would go round faster than a day. If it's further away at the same speed, it would be going too slowly, so the Earth would spin faster than it moves. So I want you to work out the distance that this satellite has to be from the surface of the Earth to maintain a geostationary or geosynchronous orbit. And that's the question I want you to do, in addition to reading the chapter and also doing the test yourself questions. Thank you for listening. Have a super Wednesday. And if you're watching this on Thursday or another day in the year or whenever, have a super day whenever you're watching it. Thank you very much. Take care.